Few months ago, your friends or relatives might have asked you in what university are you going to study? And you most probably have answered,
I have no idea!
So you took the entrance test and months have passed and the answer got clearer and clearer.
Guys, I passed the USTET. What?
Until finally you can say,
Tumasya na ako! Tumasya na ako!
Sumasya na ako!
Tumasya na ako!
even when we buy a product, we need proofs, receipts. In medicine, even patient's condition or disease needs proof, which is evident by the test results.
I had to get to the bathroom, and I barely made it there. I looked down at my legs. They had gone black.
But finally, 6 days later, the results are in.
My hunch was confirmed. Diane did have cryoglobulinemia.
Cryoglobulinemia is a blood disorder.
In mathematics, the science of reasoning called logic is used in proving theorems.
So it's a wonderful illustration of how a proof that's challenging and hard, if you try to go and prove it's contrapositive, the contrapositive, while logically equivalent, might be much easier to prove.
In our daily life, we just have to remember that whenever we give a statement, which is called an argument, we just have to make sure that we have a proof. So in this video, we're going to talk about validating arguments using the binary operations. A statement that is either true or false is called a proposition. So when we say Enrique loves Liza, that is either true or false. So that is a proposition. Smoking is addictive is also a proposition because it's either true or false. Likewise, staying late at night increases the risk of brain cancer is true or false, so that is a proposition. And when we say twice an integer is always an even integer is also true or false, so that is a proposition. So all of these are examples of a proposition. So what are the examples of not a proposition? Where do you live? Thrice a number. Listen! When we say Catriona is beautiful, that is either true or false, so that is a proposition. And when you say I am smart, that is also a proposition because that is either true or false. Now we're going to assign the symbol P for the proposition Catriona is beautiful. And when we say Catriona is not beautiful, we're going to assign the symbol tilde to negate the proposition. Similarly with the statement I am smart, and I am not smart. Note that although most use the dash with the tail for negation, in this video we're going to make use of the tilde to negate propositions. A truth table is a tabular representation of all the possible combinations of the inputs and their corresponding outputs. So when we say P, which is either true or false, then not P is false and true respectively. We may also have a compound proposition, which is a proposition which is formed by combining two or more simple propositions. So if we have a simple proposition and another proposition, we may combine them to form a compound proposition using a connectives or what we call an operation, which is either and, or, if and then, or other operations. Now, a compound proposition may also be true or false, depending on the simple proposition and their connectives. Let us take a compound proposition which is formed by two or more propositions separated by and. We call this as a conjunction, and we use this symbol. If I say I ate 1 piece of lemon and 2 liters of water every day, then I'm only making a true statement if I'm doing both. So if I don't eat 1 piece of lemon, or drink 2 liters of water every day, then I'm making a false statement. Thus, a conjunction is only true if and only if both statements are true. Otherwise, it is false. So, if we were asked to construct the truth table for not P and not Q, we may start with a column which is not P, which in this case, we're just going to negate all the values of P. So, T will become F, and F will become T. Likewise, we may add additional column for not Q, which stands for all the negated values of Q. So T will become F, and F will become T. And similarly, T and F will become F and T. And since we were looking for not P and not Q, Then all we have to do is to take a look at the last columns, not P and not Q, and using the operator AND, which tells us that this is only true when both of these are true. Thus, false and false statements will give us false. False and true statements will also give us false. And again, both true statements give us true. Now suppose we were asked to construct the truth table for not P and Q. So we may add additional column which is for P and Q. Again, which states that this is only true when both statements are true. So the first row will be true and the rest will be false. And taking a look at the last column, we just have to negate all the values of P and Q. So true will be false, false will be true, false will be true, and false will be true. Another compound proposition is what we call the disjunction, and it is used to express the word or. And we're going to make use of this symbol. If I say that tomorrow I will go to the mall or visit my friend, and if I was able to do at least one of them, then I made a true statement. Thus, a disjunction is true when at least one proposition is true. Otherwise, it is false. In other words, P or Q is false when both P and Q are false. Otherwise, it is true. So suppose we're asked to construct the truth table for P or not Q, which we may begin with adding additional column which is not Q, which tells us that we just have to negate all the values of Q. So true will be false, false will be true, true will be false, and false will be true. And to find P or not Q, we just have to take a look at the columns of P and not Q. And this operation tells us that this is false only when both statements are false. So false P and false not Q give us false, in which the rest are true. Similarly, if we are asked to construct the truth table for not P or not Q, we may start with a column which is not P, which is just the negation of all the responses of P. So this true will be false and this false will be true. Likewise, we may add additional column for not Q, which contains all the negated responses of Q. So this true will become false and this false will become true. So we may proceed with the next column, which is not P or not Q, in which we just have to take a look at the last two columns, in which this operator tells us that this is false only when both are false. So false not P and false not Q is false and the rest are true. Then if we were asked to construct the truth table for not P or Q, we may just proceed with P or Q, which again tells us that this is false when both are false. So this is true, this is also true, this is true, and this is false. Then all we have to do is to take a look at this column, in which this tells us that we just have to negate this column. So this will be false, this will also be false, this is also false, and this is true. Now what you must notice is that the truth table for not P and not Q and the truth table for not P or Q have the same results. So this indicates that not P and not Q is exactly the same as not P or Q. Similarly, the truth table for not P and Q and not P or not Q are exactly the same, which indicates that not P and Q is exactly the same as not P or not Q. And this is what we call as the De Morgan's law. The De Morgan's law simply states that the negation of P or Q is identical to not P and not Q. And likewise, the negation of P and Q is identical to not P or not Q, in which you must notice that when the negation is applied to both propositions P and Q, this operation will just be reversed. Likewise, this negation, when applied to the propositions P and Q, this operation will be reversed. Another operation is what we call the exclusive disjunction, which is only true when exactly one of P and Q is true. Otherwise, it is false. So if we were asked to construct the truth table for not P exclusive disjunction with Q, we may begin with additional column which is not P, which contains all the negation of P. in which true will become false and false will become true. Then all we have to do is to take a look at not P and Q columns to determine what is not P exclusive disjunction with Q, in which this is true if exactly one of the two propositions is true. So this indicates that this is true, this is false, this is also false, and this is true. Another operation is not AND, which is symbolized by a bar. So we say that P not AND with Q is false when both statements are true. Otherwise, it is true. So if we were asked to construct the truth table for P not AND with not Q, then we may start with a column which is not Q, which contains all the negation of Q. And taking a look at the columns P and not Q, we may find P not AND with not Q, in which this not AND operation implies that this is only false when both statements are true, and the rest are true. And suppose we were asked to construct the truth table for the negation of P, exclusive disjunction with not Q, and R, we may begin with an additional column which is the negation of Q, which is simply the negation of Q, in which all true will become false and all false will become true. Next is we may add additional column which is P exclusive disjunction with not Q, in which this operation implies that this is only true when exactly one of them is true. So since this is true and this is false, this is true. Both of them are true, so this is false. These are both false, so this is false. This has exactly one true, so this is true. Likewise, this is true and this is false, so this is true. Both of these are true, so this is false. Both of these are false, so this is false. And exactly one of them is true, so this is true. Next is we may add additional column for the negation of this. So negating P, exclusive disjunction with not Q, so all the true here will become false and all the false here will become true, which leads to this column. And finally, we may add additional column which is R, which is either true or false. And adding a last column for this proposition, all we have to do is to take a look at these last two columns. And remember that this operation tells us that this is only true when both of them are true. So since both of these are true, this is true, and the rest are false. So that's how we arrive with the last column here. Next operation we have is the not or, which is symbolized by an arrow down. And this is a proposition which is true when both P and Q are false. Otherwise, it is false. So suppose we're asked to construct the truth table for not P, not or with Q. The first thing that we have to do is to add additional column for not P, which contains the negation of P. So all true here will become false, and this false will become true. And taking a look at the last two columns here to find this one, in which this operation tells us that this is true when both statements here are false. So this will be true and the rest are false. Now, is this compound proposition and this compound proposition are identical? To answer this, we may provide a truth table for this and another truth table for this one. And if we arrive at the same truth table, then they are identical. So we may begin with P or Q, in which this operation implies that this is false when both P and Q are false. So this is false, and the rest are true. Next, we may add additional column for R, which of course R may be true or false. And having additional column for P or Q and R, in which this operation here implies that this is true when both of these are true. So since these are true, this is true, and the rest are false. Now we may check if we're going to arrive with the same truth table using these operations. We may start with P and R, which concerns these two columns here. Remember that this operation tells us that this is true when both of them are true. Since both of these are true, we know that this is true and the rest of these are false. We may also add another column for Q and R, which again states that this operation tells us that this is true if and only if Q and R are both true. So since these are both true, we know that this is true, and these are both true, so this is true, and the rest are false. And further, we may add additional column for this one, in which this operator tells us this is false if and only if both of these are false. And since all of these have both false propositions, then all of this will be false, and these are true. And what we must notice is that these two columns are exactly the same. Thus, we may say that these two compound propositions are identical. Now, let's proceed to conditional statements. In the statement, if P, then Q, P is what we call the hypothesis, antecedent, or a premise. And Q here is what we call the consequence or the conclusion. Given the example, if I am a K-pop, then I understand these symbols, which is read as annyeonghaseyo. And given these examples, we have two propositions, which are I am a K-pop, which we may use P, and I understand annyeonghaseyo, which is Q. I am a K-pop here is a hypothesis, and I understand annyeonghaseyo is what we call a conclusion. Note that if P, then Q is also called as the implication. And this is also the same as P is sufficient for Q, Q if P, Q is necessary for P, Q only P, Q when P, and Q follows from P. In the conditional statement, if P then Q, which is also called as the implication, Q here asserts that it is true on the condition that P holds. Thus, if the hypothesis is true and the conclusion is true, then the statement is true. If the hypothesis is false, but the conclusion is true, still the statement is true. If both statements are false, still the statement is true. But if the hypothesis is true and the conclusion is false, then the statement is false. Thus, we can say that an implication if P then Q is false if and only if the hypothesis P is true and the conclusion Q is false. So suppose we're asked to construct a truth table for if not P, then not Q. We may begin with a column which is not P, which contains again all the negation of P, in which this true will become false and this false will become true. We may add also additional column for not Q, in which all true will be false and all false will become true. And proceeding with this column, which implies that this is false when this is true and this is false, which when applied here, this gives us false and the rest are true. Note that if Q then P is what we call the converse of if P then Q. If not Q then not P is what we call the contrapositive of if P then Q. And if not P then not Q is what we call the inverse of if P then Q. Another conditional statement is what we call the bi-conditional statement, which is only true when both statements are the same. So if we were asked to construct a truth table for P bi-conditional with not Q, we may begin with additional column which is not Q, which again implies all the negation of Q. So true will be false and false will be true. And taking a look at these columns and applying this operation which states that this is only true if and only if both statements are the same. So since both of these are true, then this is true. Likewise, these are both false, so this is true, and the rest are false. Next is we're going to construct a truth table for if P and Q, then if P, then Q. So we may start with additional column for P and Q, which again implies that this is only true when both statements are true. So this is true, and these are false. And proceeding with if P then Q, in which this operation implies that this is false only when this is true and this is false. So this statements is false and the rest are true. And proceeding with the last operation here, which is an implication which implies that this is only false when this is true and this is false. And since none of the statements here is true here and then false here, then none of the statements here is false. So all of these are true. Consider that if a compound proposition is always true, it is called a tautology. If a compound proposition is always false, we call it contradiction or absurdity. And the compound proposition is called a contingency if it is not a tautology nor a contradiction. And an argument is said to be valid if it is a tautology. Now, is this a valid argument? If you smoke, then you have lung cancer. You have lung cancer, therefore you smoke. Note that this argument have two propositions. One is you smoke, and another one is you have lung cancer. In which assigning P for you smoke and Q for you have lung cancer, then we may transform this argument as if P then Q for the first statement, Q for the second statement, and therefore P for the conclusion. And since we have a therefore here, this indicates that these two are hypotheses and this one is a conclusion, which indicates that we have an implication. Now, given this hypothesis and conclusion, we may combine all the hypotheses with the conjunction operation. And since again this is a hypothesis and this is the conclusion, we're going to make use of the implication operation. Now, all we have to do is to construct a truth table for this argument, in which we may begin with if P then Q, in which this operator again implies that this is false if this is true and this is false. So this is false and these are true. Next is we may add additional column for this one, in which this implies that this is true when both of these are true. So since both of these are true, so this is true. Both of these are also true, so this is true. And the rest are false. And finally, we may add additional column for this argument, in which this operation again tells us that this is false when this is true and this is false. In which this is true and this is false, so this is false and the rest are true. Since the compound proposition is not always true, it is not a tautology. Hence, it's not a valid argument. Let's try another one. Is this a valid argument? If you sleep early, then you wake up early. If you wake up early, then you will not be late in classes. If you sleep early, then you will not be late in classes. In this argument, we have three propositions, which are you sleep early, you wake up early, and you will not be late in classes. Putting everything in symbol, we have if P then Q on the first one, if Q then R on the second one, then in our conclusion, we have if P then R. Keep in mind again that these are our hypotheses and this is our conclusion. Remember that we may combine the hypothesis using the conjunction operation, and since this is the hypothesis and our conclusion is if P then R, so we may make use of the implication operation. Thus, constructing a truth table for this argument, we may start with P and Q, which implies again that this is only false when this is true and this is false. In which this is true and this is false, so this is false. Likewise, this is true and this is false, so this is false. And the rest are true. We may add additional column for R, which is either true or false. And adding additional column, which again implies that this is false when this is true and this is false. So since this is true and this is false, then this is false. Likewise, this is true and this is false, so this is false, and the rest are true. Combining these two using this operation, we may add additional column in which this operation implies that this is true only when both of these are true. So since these are both true, so this is true. These are also true, so this is true, and the rest are false. And further, we may add additional column for if P then R, which implies that this is false only when this is true and this is false. In which this is true and this is false. So this is false, this is true and this is false. So this is also false. And the rest are true. And finally, we may add additional column for this argument, combining this and this, in which this operation tells us that this is only false when this is true and this is false. And since none of these are true when these are false, then all of these are true. Since the compound proposition is always true, then it is a tautology and hence it is a valid argument. Now, to help you construct a truth table easier, we have a truth table generator, which I will paste the link on the description below. So let us all fight fake news and always make valid arguments. Thank you for watching and I hope you learned in this video. If you happen to like this video, do not forget to click like, subscribe, and hit the bell button so that you will be updated in my upcoming videos.